All right, this question asks, a thin-walled hollow tube rolls without slipping along the floor. The ratio of its translational kinetic energy to its rotational kinetic energy about an axis through the center of mass is what? So what they're looking at is we have this object and it's traveling at a velocity of v. It has some moment of inertia, which for a hoop, it's a hollow tube, is going to be mr squared, where this is my value of r. And it wants to know what's the ratio of kinetic energy to translational kinetic energy to rotational. Well, translational is 1/2 mv squared. And now I have to figure out if it's moving along the floor, what is its rotational kinetic energy? Well, its rotational kinetic energy is 1/2 I omega squared. Well, this is great, except for I have i's, I have omegas. I just don't know which values, I don't know how I compares to m or how omega compares to v. So I'm going to actually make some substitutions in here. So I know that the rotational kinetic energy is 1/2 times my rotational kinetic energy, or my rotational inertia. It's mr squared. I'm rotating this thing around the center of mass, and I need to know what omega is, right? I have omega squared, so 1/2 mr squared, and my omega squared, well, if this thing is spinning at omega, that means the ground is moving underneath it at some velocity, and I know how that relates to each other. I know that the velocity is equal to r omega, or v over r is equal to omega. So v over r. And if I actually simplify this, I have mr squared, v squared over r squared. An r squared will cancel with an r squared. And I will get, at the very end, 1/2 mv squared. So my rotational kinetic energy is 1/2 mv squared, and my translational kinetic energy was 1/2 mv squared. So I get a value of 1. The ratio between the two is 1. And this works because of this moment of inertia. If we had like a solid disk that was doing the same thing, well, then the ratio would be different because this moment of inertia is not equal to our original moment of inertia. So our rotational kinetic energy would actually be lower than the original rotational kinetic energy. So in this case, the moment of inertia will actually change how much energy this thing has. But since all the mass is distributed on here, it's a surprising result, but it actually works out that way.